Okay, so once again, we're kind of looking at linking the graphs of the derivative function and the function. And we're looking at this now through the lens of the first derivative test, right? So let's see if we can come up here with, for this graph of the derivative, and that's what we've got graphed here is f prime, not f of x. That's where all the confusion sets in. If you're having any trouble with this, at some level in your brain, you're probably associating this graph with the function, and it's not a graph of the function. It's a graph of the function's derivative, right? Remember that the output of a regular f of x function is telling us the y value. Input is x, output is the y value. For a derivative function, the input is still the x value, but the output is the slope of the function for that x. Okay, so then here's where we sort of left off. Well, can you guys tell me here, where are the critical numbers for this function? Where is the derivative equal to 0 or undefined? So where is the derivative equal to 0? Just type it in chat. What are the x values where the derivative equals 0? Okay, good. Yeah, so -7, -5, -3, -1. Okay, good. Now, we want to know what's going on. So those are my critical numbers. I've got them in blue. Are there any places where the derivative is undefined? Yes or no? Okay, the question is about -2, right? Does anybody want to argue? Let's have a debate here. Debates are always good. Let's have a debate. Somebody speak up here and tell me, why would the derivative be undefined at -2? Be brave. Why is it undefined at -2, somebody? I'm not saying it is, but we're debating this. Go ahead, Ember.
Because it's a cusp.
A sharp corner?
Yes.
Okay, sharp corner. Okay, the suggestion is because it's a sharp corner. Does anybody want to argue in favor of the derivative not being undefined at -2?
I would say that it probably is defined at -2, but if you were to take the derivative again, so f double prime of x, then that would be undefined there because it's a cusp.
Okay. Everybody see that? That's correct. That's correct. So once again, if there's what the tendency is to think about this as the graph of the function, not the derivative. A derivative is undefined where f of x has a sharp corner, right? But this is not f of x. This is f prime of x, right? The derivative is defined at -2 because it has a value. You guys tell me real quick, if it's undefined, there shouldn't be an output for the derivative when we input x equals -2. But what is f prime of -2? Somebody say it out loud. I'm up at the board. What is f prime of -2?
-15.
Yeah, it looks like it's -15, doesn't it? So it is defined, right? That's a super common, it's just a natural thing to think. You see that sharp corner there and you're thinking undefined derivative, but it's not a graph of f of x, so it doesn't apply here, okay? So there are no critical numbers where the derivative is undefined. We only get critical numbers where it equals 0. So let's think about this in terms of our first derivative test, and that's kind of where we left off, right? What do we do on our tables when we have critical numbers? Well, we pick test points. We pick test points between the critical numbers, right, to determine what's the sign of the derivative between and outside of those critical numbers. So we could pick like -8. Well, at -8, the derivative, it clearly has a positive value, doesn't it? Some value clear up here. So like +15 or something, right? What about when x is -6? At -6, it looks like the derivative has a value of -3. So it's negative. Okay, what about let's pick a value between -5 and -3. How about -4? At -4, it looks like the value of the derivative is +3. I don't care about the number, I just want a sign. At -2, it looks like the value of the derivative is -15, so it's negative. And then how about at 0? At 0, it looks like the derivative is super positive way up there somewhere, right? So what's that mean then? If we're transitioning from a positive increasing function where the first derivative is positive, that means it's increasing, to a place where the first derivative is negative, where it's decreasing, then that means a peak, right? That's a relative maximum. If we're transitioning from a decreasing, we have 0 first derivatives, right? So we know we all have these horizontal tangent lines. We're going from decreasing to positive first derivative increasing. That's a minimum. Positive to negative, maximum. Negative to positive, minimum. There we go, right? There we go. And so if we had to link all those together in a function, what would that look like? Well, just something kind of like this, right? It's just going to go just something like that. We don't have to be specific about we could plug in, if we wanted to be more specific, we could plug in these critical numbers into our function, but we don't have a function, right? So we're kind of stuck here. I mean, we really don't want to get too exact. We just want to know where are the extrema and what kinds of extrema are they? What are the intervals on which the function is increasing and decreasing, right? And so based on just our little table here, we can tell all that stuff, right? It's going to increase every place to the left of -7. So for values of x less than -7, it's also going to increase between -5 and -3, and it's going to increase for values of x greater than -1. It's going to decrease between -7 and -5, or between -3 and -1, right? Okay, give me 1 to 5 on all that stuff. Make sense? Okay. Okay, let's do maybe one more of those. So there's the graph of the derivative, right? Now notice it says y equals f prime. That's the first, I've been burned by this so many times in my past. That's the first place I always look is what am I dealing with here? Is it a function or a derivative? Right, so this is the graph of a derivative. So once again, you guys tell me, is there, I want to know, let's find all the critical numbers. Okay, let's find all the critical numbers here. Critical numbers occur where the derivative equals 0 or where it's undefined. So let's look at both types here. So what are the x values where the derivative equals 0? Just type them in chat. Should be getting answers from everybody. Where is the derivative equal to 0? Okay, so everybody looked like everybody was correct on that. It's going to be where x equals 1, 3, or about 5.5, it looks like, right? So there are some critical numbers. Now, are there any places where f prime is undefined? Are there any places where f prime is undefined? Yeah, at 4, right? Look, there's a whole, there is no value of the function at 4, right? So the function is not defined at 4. That derivative function is not defined at 4. Okay. So let's do this again. And for problems like this, you might get to a point where you don't have to have the table. But for now, I think it's a good idea. For now, I think that table is useful because it gives us something that gives us a way to organize our thinking on this function. So you guys told me we had the domain appears to be, so it ends at 0. And on this end, it ends at 6. And it looks like 4 is we're talking about the function. Okay, we don't know if the function is, we don't know yet. You guys are going to tell me. Is the function defined at 4 or not? Okay, well, we know that that's a critical number. We had critical numbers at 1, 3, 5.5, and at 4. Okay, and we got to go down to row 3 to define what kind of critical numbers are those. So that's an undefined place where the derivative is undefined, and all these other ones are places where the derivative equals 0, right? So at all of these places, 1, 3, and 5.5, the places where the derivative equals 0, we know that we have horizontal tangents. That's the meaning of a zero derivative, right? So let's see what's going on. Let's pick some test points. What are good test points to pick here? What are good test points so I can apply the first derivative test at x equals 1? What could I pick for my test points? Did my voice just get garbled a second ago? Or has it been fine? It's been good, okay. What are good test numbers here? Test values for x around 1. Type them in. 2 is good. How about on the other side? Probably 0. Yeah, 0 is part of my function, isn't it? So those would be good ones. Let's pick 0 and 2. Okay. So at 0, what's the sign of the derivative? Just use your fingers. Make a plus or a minus. It's 0. Yeah, it's plus, isn't it? Okay, look, it's got a positive value. What is it at 2? Positive or negative? Negative. There you go. Whoops, that's in the wrong spot. It's supposed to be down there, isn't it? Negative. What about around 3? So we've already got one on the left at 2. What's a good test value above 3? Okay, I see some people. I saw 3.5. I saw a 4 too. Is 4 good? Yes or no? Does 4 work? No, 4 does not work, does it? Because 4 is a critical number. We have to have a test number there between those critical numbers, between successive critical numbers. We need a number between 3 and 4, so something like 3.5. Well, at 3.5, everybody agree that it looks like there the derivative is positive. Now we need one between 4 and 5.5, so what about 5? At 5, it looks like the derivative is negative. And then something between 5.5 and 6. How about 5.75? Looks like it's positive there, right? Okay, did we really even need those green numbers up there? I'd say no, right? We've got being as we have the graph of the derivative, we could probably just skip these and just see that between 1 and 3, the derivative is always negative valued and just put a negative there, right? We really don't need to put a 3.5 there because we can see that between 3 and 4, the derivative is always positive valued. Everybody get that? It'd be different if we weren't given a graph of the derivative. If we just had the derivative function, then we would have to have some test values to plug into the derivative to get those signs, right? But here, do you see that we really don't need them, right? We could do away with all those. The 0, I'm going to leave the 0 up there because that's the edge of my domain, okay? Okay, so now let's interpret this. What's going on here at this critical number at x equals 1? What is that? Okay, it's a maximum. And I would go so far, we could say one more thing about it. It's a smooth maximum, right? Because it's a horizontal tangent line, and we're going from increasing to decreasing, and it's got a tangent at 0, which means it's got to be a smooth maximum. Here we're going to have a smooth minimum, right? We're going from decreasing to increasing through a point of tangency here, right? So it looks like that. How about over here at this one? Well, we're going from negative to positive, and we've got a tangent line, so it's a smooth maximum. Now, what is going on here? We have an undefined derivative, but look at the signs of the derivatives to the left and the right of x equals 4. We're going from an increasing to a decreasing with an undefined derivative. So what the heck is that? Oh, I made a mistake here. Before we do that, I got to go back a little bit. This last one I put up here, the last one I put up here was incorrect. What should that be? Decreasing to increasing is what?
Minimum.
That's a smooth minimum, right? Okay, could this be say it again, Seth?
The first thing I said was asymptote. Now I think it's
Okay. Anybody else want to weigh in on that? If it's going, look at the derivatives. If we're going from increasing to decreasing, that means a maximum, doesn't it? Right? If the ant has a positive slope, so it's an increasing function to the left of x equals 4, and it's a decreasing function, so a negative slope to the right of 4, that sounds like a maximum. But because it's an undefined derivative, what type of maximum is it going to be? Seth? There you go. It's going to be a sharp one, right? So it's going to be a sharp maximum. Okay. So what we get here is something like that. Right? How come? Because it's undefined, but it's a point of transition of slope. Okay, and then we could just knit all those together to make a sketch of the function if we wanted to. Okay? Make sense? Okay. All right, so just one little point here. Technically, this isn't a big deal, but technically in calculus, when you say a cusp, typically you mean something like this, where it's an infinitely sharp, the slopes are vertical. Usually we would call something like this a sharp corner. So we would just do something like that, would be a sharp corner, and that's a cusp, typically. But some textbooks don't even really, it can even vary from textbook to textbook a little bit. Okay, so I'd call that a sharp maximum. Okay, last one. How about this? Determine the values of the constants a, b, c, and d in this polynomial function. Okay, here's what we're told. It has a local maximum at the point 0, 0, and a local minimum at the point 1, negative 8. I want you to come up with the values of a, b, c, and d. Okay? Before we really go anywhere, let's just go back to the fundamental theorem of algebra on this. How many unknowns are we trying to solve for? 4. Okay? So if we have 4 unknowns here we've got to solve for, how many equations at minimum do we need in a system to solve for all 4 of those unknowns? I'm seeing a 3. How many? I'm seeing a 3. Any other answers? I'm seeing a 4. Seeing a 2. Let's take a vote. Here, I know what we can do. Let's do this. Get to play with my little toys here. This is good. Let's do a poll. Okay. Put your anonymous answer. These are anonymous. Put your anonymous answer in the poll here. Let's see what we get. See if democracy works in our classroom. Okay, everybody see the results? Okay, well, we're a democracy in here, so we're going to go with 4. Okay, that's correct. That's the fundamental theorem of algebra, right? It just simply says this. We always need one way of interpreting it would be, we always need at least as many equations as we have unknowns in a system. Okay? So we're going to need to come up somehow. We have 4 unknowns. So from that information up there, we're going to have to be able to come up with 4 independent equations in our system that we could solve. Okay? I need an equation here. Give me somebody, how can I use that information? All I know is that f of x has a local maximum at the point 0, 0 and a local minimum at the point 1, negative 8.
Well, you know one of the solutions to f of x is 0.
Okay, right. So I know that 0, 0 is a solution of this equation, right? X equals 0, y equals 0. Everybody get that? Okay, so let's kind of color code this. So So here's one piece of information. It goes through that point, right? When x is 0, y is 0. So if I evaluate, that tells me, in other words, that f of 0 equals 0, right? So what's that tell me? If I plug 0 in for x, I get 0 plus 0 plus 0 plus d equals f of x, which is 0. Everybody see that? Right? Because I'm plugging zeros in there, and there, right? F of 0 is equal to 0. So that value on the left is a 0 also, right? Okay, so there's one equation. That's a good one. Tells me that d is 0. I can already fill that one in. Okay, what's another one? Well, I got another point, right? It tells me that the function goes through this point right here also, right? So that's telling me that f of 1 equals negative 8, right? Oh, sorry, f of 1 equals negative 8. So if I'm plugging in 1 for all my x's, what am I going to get? Well, I'm going to get a times 1 cubed. That's just a, plus b times 1 squared is b, plus c times 1 is c, plus d equals f of 1, which is negative 8. Okay, there's another equation. I got 2, but I need 2 more. How am I going to get another one here? Andy, how am I going to get another one? How about the fact that it's a local maximum at the point 0, 0? What's that telling me?
Not sure.
Okay. Kyle? Anybody? Yeah, right. Everybody see that? If it's a local maximum, extrema always occur at critical numbers, right? Everybody agree? Now, this is a polynomial, right? It's, A, B, C, and D are just numbers. It's just a polynomial. Well, polynomials don't have any places where the derivative is undefined, right? So the only critical numbers could occur in this case at places where the derivative is equal to 0. So let's calculate the derivative first of all, right? Is that what I did there, I'm hoping? Yeah, okay, so we took the derivative. Everybody agree that's the derivative? I'm just differentiating using the power rule term by term, right? So the 3 comes down, 2 comes down, right? So we just get that. There's my derivative function. Well, the fact that this is a maximum, I have a local maximum at the point 0, 0. What's that telling me? That's telling me that f prime of 0 has to equal 0, right? Has to be a critical number there. So if I plug 0 into my derivative function, I'm going to get a 0 there, 0 there. All I'm left with on this side is a c, and f prime of 0 is 0, so I'm plugging a 0 in for that whole thing. So I know c is 0. Okay? What about this last little piece here? So we've got a local minimum at the point 1, negative 8. So that's telling me that f prime of 1 is equal to 0. So if I plug a 1 in for x in my derivative function, f prime of 1, I'm going to get 3a times 1 squared plus 2b times 1 plus c equals 0. Okay, so that gives me, look at that, that gives me a 4x4 linear system, right? And I really, now this is a pretty easy one to solve. I don't even have to use matrices on this one, right? Because I already know that D and C are 0, right? So I can just do this. I know that's 0, that's 0, that's 0. And then this whole thing, I really only end up with 2 different equations here. I get A plus B equals negative 8, and 3a plus 2b equals 0. And so now I can solve that 2 by 2 system pretty easily. I could just do, how about if I just did, I could just multiply the top one through by -2, right? I can use elimination here. If I multiply the top one through by -2, I would get -2a minus 2b equals 16. I've got the other equation, 3a plus 2b equals 0. If I sum those two, the b's cancel. I get a equals 16. I can plug that back into, and let's plug it back into my original equation right here. A plus b equals -8. So I get 16 plus b equals -8. If I subtract 16 from both sides, I get b equals -24. So I got my answer, right? My original function then is, I got a is 16 and b is -24. Okay, everybody see that? See if we got it right. Hope we did. Oh, we did. Good. Is that what we got? 16? Yeah, 16 -24. Okay. Quick review. Do you guys remember how to solve a linear system? What if those middle ones weren't so simple? What if they weren't 0? C and D weren't 0, right? Then I could set this up on Desmos. You guys haven't seen this yet because we didn't have this a couple of years ago. I'm going to show you something cool on Desmos here. So there is a new calculator on Desmos, the Desmos matrix calculator. And if you just Google Desmos matrix, you'll get it. Okay, there's my equations, right? Okay, first of all, if I wanted to write this, I would have to write this as all of these equations in standard form, right? So in standard form, we're trying to solve for A, B, C, and D, right? So I would have to put the A's first, then the B's, then the C's, then the D's, and then I'm gonna use an augmented matrix where I'm going to have 4 rows and 5 columns. Then I have a 5th column for the whatever's on the other side of the equal sign for the constants, right? What the heck happened here? Oops. Oh. Whoops. Can you guys hear me?
Yeah.
Okay, whoops, sorry about that. So how long was that gone? Okay, so let's go back here. So Desmos, what I was saying, Desmos has a new matrix calculator. If you want to get the matrix calculator, you just Google Desmos matrix. And here's what you get. So I've just got to take this linear system and express this as an augmented matrix, right? As a matrix that has all of the coefficients. It has a column for each coefficient, and it also has a 5th column for the constants, right? And I've got to write all the equations in standard form, so my variables, my unknowns, A, B, C, and D, are going to be in order. So this first row is pretty boring, right? All I get here is 0A plus, whoops, how's that? Finally, we got it. Now, everybody can see it now, I'm hoping. All right, there we go. So here's my Desmos, just Google Desmos matrix, and it gives you this calculator. So here's our linear system, right? We've got to write this as an augmented matrix where we have 4 rows, 1 row for each equation, but 5 columns. First column is going to be for the coefficients of A, then the coefficients of B, then the coefficients of C, then the coefficients of D, and then the 5th column is going to be for the constants on the other side. Okay, so let's first of all set up our matrix in Desmos. We want to do, we're going to go down here and do new matrix, and then we get to choose for this matrix how many rows and how many columns. Well, we said we wanted 4 rows and 5 columns, right? Let's do our first row. So our first row is the equation D equals 0. Well, D is the same thing. D equals 0 is the same thing as 0A plus 0B plus 0C plus 1D equals 0, right? Everybody agree? Okay. Next one. That's the red equation here before I cross stuff out, right? So we've got 1A plus 1B plus 1C plus 1D equals -8. Okay, next row, C equals 0. Well, really that's 0A plus 0B plus 1C plus 0D equals 0. Next row, 3A plus 2B plus 1C plus 0D equals 0. Okay, so there's my 4x5 matrix. Okay, now what? Now that I've got my matrix, let's see here. So now I think I got to go enter. And then it's called matrix A. So then I'm just going to do reduced row echelon form of matrix A. And I have to use this A down here because these are the matrices I can build. Reduced row echelon form of matrix A is right there. Okay, well, what's that telling us? Let me take a picture of that. In fact, let me take a picture of all this stuff just so you guys can see this a little better. There we go. So what's this telling us? There's our answer. If I do reduced row echelon form of A, that first row is just telling me that 1A plus nothing else equals 16. So that's just telling me A equals 16, right? How about this one? That's telling me 0A plus 1B plus 0C plus 0D equals -24. This one tells me that 1C equals 0. This one tells me that 1D equals 0. So there's all my solutions. Okay. Pretty slick, huh? Okay. So I'd be willing, give me some feedback here. On the at-home tests, do you feel like you need a day? We only have one other day this week, so I'm really not excited about doing this, but if you need it, I'll let you have it. Do you need Thursday some extra time to work on the tests? Yes or no? And if you do, you do. Just be honest. I mean, just, I would prefer, of course, just because we're so limited with our days, I would prefer to take as little time testing as possible, but we haven't taken any time on this test in class. So if you need a day, I'm okay with it. Just let me know in chat. Yes or no. If I get some yeses, I'm probably going to go ahead and give you the day. Half day, okay. That's a possibility. Here, let's do it this way, just so you guys don't have to. I'm going to make it, let's make it anonymous. How about? I'll make a poll. You guys can answer with a poll here. So,
Mr. Oya, did you extend the due date to Monday?
I did. Yeah, everybody saw that, got that email, right? Okay. Okay, there's your poll. You can anonymously answer that poll. Okay, so we'll go work day on Thursday. Okay, work day on Thursday. So you can plan on that. That hopefully that takes, that makes sense. I'm okay with that. All righty. I'm gonna let you go a minute early here. Oh, actually 5 minutes early. That's fine. Any questions, anything? Okay, I'll let you go a few minutes early, get up, stretch, get a snack real quick for fourth period. Have a great day. I will see you on Thursday for a work day. I'm here after school if you need any help on anything. Bye.